So now that we finally made it to section 5.2, we can have the proper definition of the integral. And we're going to have two of these, I guess. We're going to have the log one, and then we're going to be able to have a condensed version, which is going to be super useful for us. So first up, we have a partition of an interval. A partition of the interval from a to b is simply a set of points in increasing order, x0, x1, x2, all the way to xn, that are all contained within the interval. And the reason it is defined that way is because I can divide up the interval into a union of each pair of these points. And we'll say a partition is tagged if we can choose a point xi star from each subinterval. So given an interval from a to b, a tagged partition, I could draw out looking like this. And somewhere out of this first interval, I'll pick a random point. It doesn't have to be random. You could be one of the endpoints or somewhere exactly in the middle or anything inside of it, really. I'll have an x1 star, and somewhere out of the second interval, I'll have an x2 star, and somewhere out of the third, an x3 star, out of the fourth, an x4 star, and out of the last interval, I'll have an xn star. And this here would be a tagged partition of the interval. So, we say a function is integrable on an interval from a to b, and we'll write this notation: the integral from a to b of f of x dx is equal to L if, for any epsilon greater than 0, and for any tagged partition of my interval from a to b, if delta x is equal to the maximum subinterval width of my tagged partition, then there exists a delta greater than 0, such that if as long as delta x is less than delta, then L minus the Riemann sum there is less than epsilon, which looks absolutely awful, right? But in short, it says that the limit as n goes to infinity of the sum I equals 1 up to n of my interval widths minus xi minus 1 times f of xi star, no matter how I chop up my interval and choose my sample points, I'm going to have the limit of this Riemann sum. Here I have the width of each subinterval, or rectangle, and here I have the height. This limit should be equal to L. And this is supposed to happen regardless of how I choose to cut up my function in my interval. But it's this is really hard to use, and no one wants to check an infinite number of ways to partition an interval to make sure that the integral is going to work. So we have a fact to bundle along with this to make our life phenomenally easier, and this is something which is provable, but we just don't want to. If f of x is a continuous function, except possibly at finitely many points, and bounded, that is, there are no vertical asymptotes, for example, then f must be integrable. There are other situations where a function might not satisfy these conditions, but it'll still be integrable, and we'll deal with those in another class. But for now, these functions I can guarantee are going to be integrable. So pretty much all the functions we've been dealing with already so far, except for like 1 over x. I should be able to find the integral of natural log of x as long as I don't start or include the x equals 0. I should be able to find the integral of sine of x, cosine of x, pretty much any of my polynomials. I could do 1 over x as long as I don't include 0 in my interval here. But also I can do a bunch of weird looking piecewise functions as long as nothing too crazy happens. But since I know a priori that these are going to be integrable, that means regardless of how I set up my Riemann sums, as long as I throw them into a limit, I'm going to get the integral. I'm going to get the actual answer. So if f of x is already integrable, then any Riemann sum will work for finding the integral as long as the delta x goes to 0. And again, that delta x is the width of the largest subinterval. I can cut it up however much I like, but the parts need to go down towards 0 as long as I end up going to infinitely many rectangles. So what this means is that the integral from a to b of f of x dx is equal to, I can use either my left or my right or my midpoint formulas for Riemann sums. My favorite is the right hand, so I'm going to start with that one. Limit as n goes to infinity of the sum I equals 1 up to n. Here the delta x is just b minus a over n. My delta x is just b minus a over n because each of my subintervals are going to be equally spaced. And my heights, my sample points, are all going to be on the right hand side of the interval. So my heights will be f of a plus I times b minus a over n. And this would be equal to, I get the exact same value if I use the left hand rule. So let's label this. This is the right hand. This is the left. I can rewrite the left as a sum from 0 to n minus 1 b minus a over n times f of a plus I times b minus a over n. So you can see the major difference between the right and the left is, depending on how you write it, you can keep the bounds and change this I to an I minus 1, or you can keep the I and change the bounds to 0 to n minus 1 in place of the 1 to n. But again, I typically prefer to use the right hand rule all the time because it's simplest to keep track of. And the theorem says that I can do that without any problem. And I would get the same value if I use the midpoint rule. Now, since we've defined the integral, we can collect some properties. It's just like how the derivative has some properties. The integral of a constant, or let's just say the integral of 1, is equal to b minus a. Because 1 is a constant function. If I try to find the area under this curve, I'm going to have exactly the area of a rectangle, which is going to be width, which is the length of the interval, b minus a, times height, which is 1. If I have a constant multiple of a function and I'm trying to take the integral of that, then this is going to be the same thing as a constant multiple on the outside times the integral. And this basically works simply because the integral is the same thing as a summation, which is just a sum of things. So this is kind of like factoring off the c off of every term. And 3, if I have a sum or a difference, difference works okay. This is the same thing as the sum of the separate integrals. Difference is okay. A to b, g of x dx. But there are more. Let's see, that's 3. Here's 4. Integrals have a property we like to call independence of path. It doesn't matter where you go. What matters is where you start and where you finish. So if I have the integral from a to b of f of x dx plus the integral from b to c of f of x dx, then this will be equal to the integral from a to c f of x dx. Because here I started at a, went to b, and then started at b and went to c. So in the end I started at a and finished at c. And that's all that really matters in terms of the integrals. This also allows me to split my integral into 2 parts if I find something halfway in between, which is useful in some cases. 5. If f of x is positive on a to b, then the integral must be positive. But the same is true, actually, for negative functions. So if I was less than or equal to 0, this would be less than or equal to 0. And the reason for that is, if we think back to the Riemann sums, I'm supposed to be adding up the areas of a bunch of rectangles. But if my function values are all negative, my widths all stay positive, but my function values are negative, which means my heights are negative values. So when I multiply the width times the height of the function, I'm going to get a negative rectangle area. And if I add all those up, I'm going to get a negative area under the curve, which I'll get to in a minute. But if f of x is less than or equal to g of x, then the integrals will follow suit. And if my function is bounded, if it's dominated, then this kind of follows from the previous property, but I'm going to have m times b minus a will be less than or equal to the integral, and that'll be less than or equal to big M times b minus a. Who knows if we'll end up needing this, but it's true. So let's try using one of these things. Let's look at f of x equal to x times x plus 1 times x minus 1. This is equal to x cubed minus x. And I want to look at two things. I want to find the integral from from 0 to 1 of f of x dx, and b, I want to find the integral from negative 1 to 1 of f of x dx. Which means something special is going to happen. So for a, the integral from 0 to 1 of x cubed minus x dx, I could split this up into two integrals, the integral from 0 to 1 of just x cubed minus the integral from 0 to 1 of just x, but probably won't do me a whole lot of good right now. We're going to be using that property a whole lot more in section 5.3. So this should be equal to the limit as n goes to infinity of the Riemann sum. And again, I always like to use the right one, and in fact the book goes ahead and uses the right hand rule as the bottom line for us to use. B minus a is 1 divided by n times the function evaluated at 0 plus 1 times 1 over n, or I times 1 over n. So I have 0 plus I times 1 over n cubed minus 0 plus I times 1 over n. And I just need to evaluate this limit as n goes to infinity. I'm actually going to treat this kind of like I did the one yesterday. First, I want to look at what I have inside of my sum. I want to 1. Multiply everything out. 2. Distribute my sum across all the terms. By that I mean the sigma thing. And then 3. Out of each of my new sums, I'm going to factor out anything that's not an I. That leads me to step 4, where I can use those additional facts from yesterday to replace any sums that I can with those closed form formulas in terms of n. And then finally, for 5, I'll be able to evaluate the limit. So, let's do that. 1. I'm going to multiply everything out. So this is I over n cubed minus I over n, leaving me with, let's see, I cubed over n to the 4th minus I over n squared. Now I want to distribute my summation across all the terms. And then out of each of the terms, I'm going to factor out anything that's not depending on I. So let's see, I'll have the i's stay, the n can come out. So this is 1 over n to the 4th times the sum I equals 1 up to n of I cubed minus the n's can come out, the i's have to stay, and these guys, they have formulas, which I'll make available once we get to the test. So 4, I'm going to replace those summations with the formulas, so I'll have 1 over n to the 4th there. I cubed, the sum from 1 to n of I cubed, gets replaced with n times n plus 1 over 2 quantity squared minus 1 over n squared times the sum from 1 to n of I gets replaced with n times n plus 1 all over 2. And now I need to do work to evaluate my limit, which means I'll have to multiply all this stuff out. So let's see. If I distribute the squared over here, I'm going to have n squared times n plus 1 squared all over, looks like I'll be left with 4 times n to the 4th, minus, over here, I'll have n times n plus 1 over 2n squared. I can cancel some stuff to make my life easier. There's 2 n's, so those go away. Here's an n, so one of those goes away. Now it looks like I'm left with n plus 1 quantity squared over 4n squared minus n plus 1 over 2n. Now I have lots of options trying to evaluate these limits because technically what I have here is rational functions of polynomials in n. I have the letter n instead of an x, but it all still works out. So I could just find the highest powers in the numerator and denominator and compare those, but for now I'm just going to go through, multiply everything out, and split up all the fractions. So if I multiply out n plus 1 quantity squared, I'll have n squared plus 2n plus 1, and that's all over 4n squared minus n plus 1 over 2n. So you can see here where I can take advantage of the coefficient thing for evaluating these asymptotic limits. So I should expect to get 1 over 4 minus 1/2. But if I split up all these fractions, I'll have n squared over 4n squared plus 2n over 4n squared plus 1 over 4n squared minus n over 2n minus, because that distributes, 1 over 2n. And then a bunch of stuff cancels, leaving me, after evaluating my limit, actually, with 1 over 4 plus 0 plus 0 minus 1/2 minus 0, giving me a final answer of negative 1 over 4. Now, I've said before that the integral is supposed to be the area under the curve, but what happens if the curve is the thing that is under? Well, this function looks something kind of like this. Over here, from 0 to 1, my function is below the x-axis. The integral is supposed to be the area under the curve, but the curve is under the x-axis, so I get negative values. But also, since I'll be adding up a bunch of rectangles with a negative height, giving them negative areas, I'm going to end up with negative values. So, in the integral, area above the x-axis is going to be positive. Versus area below the x-axis is going to end up being negative. So what could potentially happen is, depending on the shape of your function, you could do an integral on some interval, and you get an integral equal to 0. And we're actually going to see that happen. Because if I do part B from above. I want the integral from -1 to 1 of f of x dx. So the f of x is actually x cubed minus x. Not x. N. The sum I equals 1 up to n. What should this look like? B minus a over n is now 2 over n. And my a plus I times b minus a over n is equal to -1 plus I times 2 over n. So I have -1 plus 2i over n, quantity cubed, minus -1 plus 2i over n. And I'm unfortunately going to have to multiply all of this out to finish off my problem. So for this first one, we have some advantage with Pascal's triangle. I should get -1 plus 3 times 2i over n minus 3 times 4i squared over n squared plus 8i cubed over n cubed. Plus, since a negative and a negative will cancel, so plus 1 minus 2i over n. And just because I can, why don't I go ahead and factor this 2 over n outside of my sum first. I have -1 plus 6i over n minus 12i squared over n squared plus 8i cubed over n cubed plus 1, so the -1 and 1 will cancel, minus 2i over n, which I guess I can combine with the 6i over n to get a 4i over n. So now if I distribute my summation, that's gone, that's changed, so I have the sum I equals 1 up to n of 4i over n minus the sum of 12i squared over n squared plus the sum of 8i cubed over n cubed. And I have to factor everything that's not an I out of each of those sums. So I have 4 over n, sum I equals 1 up to n of I, minus, 12 over n squared times the sum of I squared plus 8 over n cubed times the sum of I cubed, which is a neat function because it actually uses all 3 of those interesting summation formulas. So I have 2 over n multiplied by 4 over n times n plus 1 over 2. That cancels. Minus 12 over n squared times n plus 1 times 2n plus 1 all over 6. And take care of that and that, plus 8 over n cubed times n plus 1 over 2 quantity squared. So let's try to clean some of this up. I have 2 over n. I'm left with 2n plus 2 in the first term over 1. We'll keep that. Minus 2 times n plus 1 times 2n plus 1 all over n plus 8 over n cubed times n squared times n plus 1 squared all over 4. So now let me finally redistribute this 2 over n. I have 4n plus 4 over n minus 4 times n plus 1 times 2n plus 1 over n squared plus 4 times n plus 1 squared all over n squared. So if I try to evaluate this limit, let me multiply everything out first. I don't want to make a mistake. Up here, I'll have 8n squared plus 12n plus 4 all over n squared plus 4n squared plus 8n plus 4 all over n squared. So it looks like, after I evaluate my limit, I'm going to get 4 minus 8 plus 4, which is equal to 0. This is because the area above the x-axis on the left side of the curve is equal in value to the area under the x-axis on the right side of the curve. And this is actually something which always happens for odd functions. The integral of an odd function on a symmetric interval from minus a to a is always equal to 0, because the function values on the right are mirrored on the opposite side on the left, and so your area below on the left or above, if the case may be, would be equal to the corresponding area of the negative sign on the right. So similar along those lines, there's actually a couple of other special properties. 8. The integral from a to a, if I go nowhere for my integral, then I will have gone nowhere. I'll have 0 for this integral because my start and end point are the same. So my total change is nothing. And 9, if I flip my bounds, if I go from a to b, if I flip my bounds, it's the same thing as multiplying by -1, b to a, f of x, dx. And the basic reason for that is this. If a to b is forwards and positive, then b to a is backwards and negative. So all of my little dx's in my Riemann sums are now going to be negative because I'm going through them backwards. So flipping the bounds is going to be the negative value of the original forwards direction integral. So I could ask odd questions like this. If the integral from 1 to 3 of f of x is 5, and the integral from 1 to 7 of f of x is 9, what is the 3 times the integral from 3 to 7 of f of x? And there's 2 different ways I could approach this problem. I could say I need to start at 3 and go to 7. So the integral from 3 to 1, for example, of f of x dx, this would be equal to -5. And the integral from 3 to 7 of f of x dx would be equal to the integral from 3 to 1 plus the integral from 1 to 7, because I start at 3, go to 1, and then go from 1 to 7. So in the end, I've gone from 3 to 7. Which means the integral from 3 to 7 of f of x dx is equal to -5 plus 9, which is equal to 4. Which means 3 times the integral from 3 to 7 of f of x dx is equal to 12. Alternatively, and this is actually going to be exactly the same amount of work, just in a slightly different order, I could have said, hey, the integral from 1 to 7 of f of x dx is equal to the integral from 1 to 3 of f of x plus the integral from 3 to 7. I go from 1 to 3 and then I finish it off the rest of the way from 3 to 7. But I know that the integral from 1 to 7 is equal to 9, and I know the integral from 1 to 3 is equal to 5, but what's missing is the integral from 3 to 7. So I'll just solve for this integral in this equation here. I'll get the integral from 3 to 7 of f of x dx is equal to 9 minus 5, which is 4. And then I achieve the same conclusion as I did over here, that 3 times this integral is going to be equal to 12. This covers the essential definition of the integral, but what we're going to find out next time is that the integral is a lot like taking an antiderivative. In fact, it's the same thing. That's what the fundamental theorem of calculus provides.